Wow. Wow.
There we go.
Today we're talking about high energy physics. Wow.
High energy physics, and it's great that we're finally doing a little science like episode, and we're joined by the show's very own Neil deGrasse Tyson-esque guest.
Dr. Amin Abou Ibrahim. Thank you.
I'm not aware of that. Thank you. Thank you, guys.
Episode
We like to
153.
put our guests on the spot. We do
of
that
the
a lot.
A2
By
show.
the way.
Oh yes.
We do that a lot. We like to put them. It's the funniest reaction sometimes. So
Amir's back.
Sounds
Thanks,
good.
Amir, for joining us once again.
Yeah.
Well,
Thank you, guys. My pleasure.
Hello.
All right.
See,
yeah.
this is a special episode because this beautiful person right here used to be these two's teacher in school,
Yes, in
right?
high school.
And it's pretty
the
cool.
last lesson in physics I had was probably with you. So let's continue on with another lesson in physics.
Yes.
I mean,
Wow,
can you
that's-
tell us a
that's
little bit what do you do? Yeah.
So I'm in theoretical high energy physics, or sometimes known as particle physics. So, because I mean, in theory, in the theoretical sort of framework, we try to come up with models that explain unknown or phenomena in physics, or something that we see, in nature. That's we try to explain. Now,
What is a particle? Sorry.
Well, okay, good question. The particle that we're talking about is the fundamental building blocks of the universe. So it's basically the smallest constituents of matter. So I'm sure everybody has learned this in school, that electrons are a fundamental particle. So atoms are not fundamental. You can break down an atom. Even a proton and a neutron are not fundamental. You can even break them down further to quarks. Now, quarks, so far as we know, up to this point, are fundamental particles. You cannot break them any further. So, and those are the things that I study, that I do my research in, are particles that make up the,
So you
our
study
universe.
quartz, right?
Study quartz. Mm-hmm. So yeah. So
Their nature and
their
everything,
nature.
and like what they are like out there in the wild. So
I want to hear a myth busted by you. What is I hear string theory, I hear like 7 dimensions, and like you can travel between space and time. Maybe that's wrong. I don't know. I have made from the movies, right? So what is string theory?
So, all right. So a little bit of context. The main issue we have in physics, as many some people know, that we're trying to get the two worlds, two different worlds actually, to come together, which is the particle world, the very small, where quantum mechanics is prevalent, is actually the dominant law of nature, and the macroscopic. Basically, we're talking about the galaxies and stars. This is where general relativity is prevalent. So we're talking about the very big and the very small. The main issue in particle physics is that we cannot marry these together. That's the main issue, which is sometimes known as unification. And we try basically to come up with models, with theories, in order to unify those two. Now, one good candidate to unify the very big, the general relativity, with the very small, quantum mechanics, is string theory. Now, string theory has many problems with it, but in brief, we think of particles as made of strings, or actually there are strings of a certain energy or a certain frequency, and their vibrations or their energy will manifest itself as, let's say, the mass. For example, if we view an electron as a string, it has different vibrations than a quark, and that's why it has a different mass or different properties.
Sorry for asking, but like, what do you mean by string? String as in string, or like, is there
right? A string is more of a mathematical, quantity.
Oh, so it's not like a literal string. When they say string theory, they mean like a mathematical thing.
Well, yeah, well, sure, but the thing is, to actually know what a string is exactly, you need to do an experiment in order to basically measure or to actually see a string, and we cannot do that.
And
not
the way they
that
did it is
moment,
using that huge thing in Switzerland,
a collider.
Hadron Collider, yeah.
Hadron
The
Collider, that
LHC.
was made by Professor Michio Kaku, who I was a fan of in my youth, until I realized physics was not for me.
Yeah, well, I don't know if it was made by him. It was not made
I
by
mean,
him, but
he helped in the whole. I think he was very responsible in the whole like matters of the Hadron
Well,
Collider, if I'm not mistaken.
there's a lot of there's a lot of people who put their who had their input in there from theory and from experiments. So there's a whole bunch of people.
But you've seen the string, or like they found the string, or
No. The string, in order to actually probe that that length scale, we're talking about a Planckian. We call it a Planckian length scale. Basically, we need colliders that are that have energies that are unattainable. Not now, not in the near future.
Oh wow!
It's so some people even think that we will never attain that energy. It's a humongous amount of energy. So probing, getting a glimpse into string theory is not attainable, not now, and probably not in the future. But of course, we can get to scales now. We can see, of course, the quarks and all the fundamental particles. The last one was the Higgs in 2012.
Okay.
So yeah, string theory is more of a.
So wait, they've actually seen the imprints of a quark, like the quark's energy. Like
so the quark, right? So the thing about the quarks are they do not exist in the free state in nature. They are always a bound state. So you cannot see a free quark roaming around. They're always bound together. They bind together to form mesons or baryons, or some of a baryon like a proton or a neutron, for example.
Which is the smallest one?
So the smallest one is the quark, but you cannot see the quark.
No, I mean the smallest one that you can see.
Exactly, like a meson or a baryon, which is a proton, for example. Exactly, yeah. That's a very weird thing about quarks, and that's why they're very difficult realm of particles. On the other hand, you can see an electron. That's an electron does not have to bind with other. It can be a free particle.
I see.
Just like a muon or the other guys.
So they've been trying to like combine the general physics with particle physics using the string theory, but you say it's like too iffy. We don't have enough evidence for it yet. So is there like a different way about it?
Now, a lot of my friends who are string theorists, we always sort of like, slash. I have my opinions, and
their work is a hobby. Yeah?
They are very much. Some of them, they're very much detached from reality, from the experimental world, which is fine. I mean, they're pure theoretical physicists, and it's fine. But what I love is to actually do theory and then take that theory and test it in real life and see if it can predict nature, or it can explain actually things that we have seen before, and it can predict. This is the power of predictive science. When you have when you do a model in science, that's something that we learned in 8th grade. That when you write up a mathematical model, that model should be able to explain existing phenomena, and it should be able to predict. So string theory can do both, but it cannot actually be tested in an experiment. So there are some aspects of string theory that can explain existing stuff, which is great about it, and that's why people get so hyped up about it when it came into light around the 80s, I think, the 70s or in the 80s. But then it got so ramified into so many branches that it got so complicated, and I think a lot of people got lost into the abstract mathematical complexity of it, that sometimes people forget that what we're trying to do here is to explain nature,
practical
physics.
Explain nature. Oh, I see.
Yeah.
Wow.
But it's a very nice, attractive idea.
Nice idea. I mean, I want to ask you a fun question. This is a fun question. So like, I know, like you said, you want to, or you want to practice more experiments, right? And take the theoretical, put it into experiments. Let's say we gave you like a quasi-infinite budget, and you can do any experiment you want, right? What is something you'd like to? What's an experiment you'd like to design and see?
Well, a part of why I'm a theorist is because I do not have the imagination of coming up with experiments. So I do theory, and you know, I give the experimentalists the model, and they're like, there we go, you can just make an experiment.
But you can get creative with your theory, right? Is that like you can think outside the box? And
sure, that's what we do. But if I can think of something, is actually building a more powerful collider. And this is one of the things that CERN and other groups are pursuing right now. I think the next big collider might be built in China. And also there's another one which is a little smaller that they're trying to build in CERN in Switzerland. So that is something, and you know, negotiations take a long time because of funding. You know, you have to convince people with money, like in this case, the European Union. You have to convince the European Union that you need the money in order to build something like that. That's why negotiations take some time. So I have.
Well, they have the opportunity to call it the Great Hadron Collider of China now.
Yeah, that's right. That's right. And it will be very powerful. It will be 100 TeV basically.
Oh wow. I don't know what that means, but that sounds like a lot. 100.
Right. So what we have right now is 14.
Oh,
so
14.
We're going
wow.
from 14 to 100. So
that's a lot. That's a big.
That's a big jump, and so that's.
I don't think I'm comfortable with China having anything. If I'm being honest, I mean, like
anything that powerful.
like China on its own is already like bad shit crazy, right? But like giving them something like that, wouldn't they be able to come up with a kind of weapon?
I don't know.
To, you know, because China's weaponry system is crazy, so it's like.
Yeah, well, the same thing with the U.S. as well. I mean, why do you trust the U.S. and not China?
With NASA.
They didn't trust both. That's China. Why they put it in Switzerland in the first place, right? Like they're like, not you, and definitely not you.
They put it in some like a neutral sort of the country with no conflict.
They should put it in Kuwait. We rarely get
put in Kuwait.
Well, we don't get involved in anything. It'll be safe with us. Plus, we can afford to maintain
that
it.
That is true. You should pitch it.
Well, if it makes you happy, Jordan is part of Jordan is actually a member. It's an observer state in CERN. So they can they put money, and they also send their scientists to CERN, and that's a good thing. Unfortunately, Lebanon is not. The U.S. is a member state, so they actually Also, no, the U.S. is also an observer state, but they put money into CERN. But the other European unions are actually member states.
I see. So when you're taking it from 14 to 100, what are the things you're looking for? Like or the things you expect to find? Right. So
you asked me first, like what's basically my kind of research, and when I say theory, of course, it's a very broad topic. In particular, what I work with is supersymmetry, and supersymmetry is this theory.
That sounds
right. Is this theory that tells us that for every particle that we have in nature, there's a heavier copy of it, of a different spin, basically.
Like what was it? H2O and no, the heavier version of hydrogen. It starts with a D.
Deuterium and tritium.
That's the one. Yep.
Yeah. Well, those are elements. Those are atoms. Those are for us. Those are large objects. What we do is fundamental physics, which is basically looking at the very small particles. So when I talk about supersymmetry, I'm talking about fundamental particles that we haven't seen before. For example, the electron has a certain spin, and the supersymmetric partner of an electron is a scalar electron, which is heavier, which is something we haven't seen before. So what we basically do is we duplicate the number of particles in nature and they are heavier, and that's what we call supersymmetry. This is a very sort of simplified version. If I don't want to go into the boring details of it. So those heavy particles need more powerful colliders to be created. Now, we were hoping that we could see something at the LHC, but so far we haven't seen anything. And that's why we're actually going to higher energies. So to answer your question, if we go to 100 TeV rather than 14 TeV, we might be able to create those heavy particles and eventually see them. You know, and that would be something great. But
great because
you're basically you're building something so big to look at something so small.
Very small. Absolutely.
Oh, wow.
Yes. That's exactly. It's that's a nice way of putting it.
It's pretty cool.
Is it great just because it's like pushing science forward, or is there like a practical reason behind?
So the reason is the model that we have that explains the universe is incomplete. So which is basically the standard model of particle physics, we call it. The standard model we know is very precise. It has very accurate predictions, but it cannot explain everything. One of those things is dark matter, for example, or dark energy. Even the masses of the neutrinos, those things are, even gravity as well. All of these are not part of the standard model.
Okay.
So supersymmetry is one of those candidates that can explain, for example, dark matter.
Oh, wow.
So if you were able to observe a supersymmetric particle, that would be something great. So we would be getting closer and closer to
understanding gravity.
Probing, you know, or dark matter, or
dark matter.
You know, the things that the standard model does not explain.
I see.
Yeah.
Can you tell us a little bit about dark matter, actually?
Right. So now, if you take, for example, the amount of matter that you have in the in this universe. Okay, let's start from the story from Newtonian mechanics, something that everybody learns from school. So if you take Newton's law of gravity that says that the force is proportional to the mass, do you guys still remember that?
Yeah.
It's like number one, I think. Or number two, maybe three, maybe. I'm not sure.
Well, no, I'm talking about the law of gravity, which is
neither one of them.
which is none of those.
You guys can now understand how well I did in physics back in school.
All right, good
Yes.
job. You'll learn.
W
equals mg.
Weight
Yes,
equals-
this is
that
okay.
sounds
Yeah, that's
gravity,
the weight
yeah.
on force of weight on Earth. But if we're talking about planets, you know, we have two planets, so there's a force of attraction between them because they have a certain mass. So basically, the bigger the planets are, the bigger the force of attraction between them. So if you take the Newtonian mechanics and apply it to galaxies, so let's say you take a spiral galaxy, which is, for example, the Milky Way, and you calculate the amount of matter in the Milky Way, which is basically how much stars are there, dust, the planets, everything. You just put them all together.
Is that quantifiable though? Like everything in the universe?
Yeah, you can calculate the mass of objects like that. It's crazy, I know, but you can do that. Yeah,
Damn.
it is. So, and then if you try and calculate the rotation speed of the galaxy, you will see basically that the further you go away from the center of the galaxy, the rotation speed increases and then starts falling down, because the biggest amount of matter is more concentrated towards the center. So you move further away, you have less and less matter, and so on. So this is what Newtonian mechanics predicts, that the velocity of the galaxy should rise and then drop. Yeah. But when you go in and then you measure this by experiments, you see that the rotation curve goes up and then keeps going up and up and up. Keeps increasing.
Strange. Yeah,
it is very strange. And the reason behind this is that there is an invisible matter there. There's a certain matter that you cannot see, which grows linearly with distance. So as you go away from the center of the galaxy, there must be some matter which is piling up that you don't see.
Oh.
So basically, you have the disk of the galaxy, there's a halo around it of mass that's invisible to us. And this halo is basically dark matter. So dark matter is a matter that has mass because it has a gravitational effect on other objects, but we cannot see it because it does not interact with light. And that's why it's called dark.
I see.
Yeah, it's there. We know it's there,
Yeah.
but we don't know what it's made up of. That's the main issue.
Do we know if it interacts with anything at all, actually?
Yes, it has very weak interactions, and that's why we have experiments on Earth that are trying to detect dark matter. One of the experiments that actually saw a glimpse or something. There's a hint of something happening. That there was a paper out 2 months ago that we're working on right now as well to try and build a model to explain this. They saw a hint of a particle that could be dark matter at this experiment. So this experiment is a laboratory underground in Italy, not too far from here. And what they do is like they have this huge tank. They fill it with liquid xenon. Xenon is a very heavy element. So what happens is that a dark matter particle will go through the air. It will go through this huge container, which is underground, and it will pass through the xenon. So as it goes through the xenon, it will knock off electrons from it.
Oh, wow.
So the electrons will be picked up by something we call photomultiplier tubes, and a current will be generated, and you can see a signal basically on the screen. So what they saw a couple of months ago, they saw a signal at a certain energy that they could not rule out. So basically, there is something there, but it needs more study to figure out if it's really dark matter or it's something else which is causing this signal. So that's something very exciting, and we're actually working on right now to see if we can come up with a theoretical model to explain this success.
Just out of curiosity, the currents that they get, like in what range are they? Like they must be really, really low in the microns.
Oh yeah, exactly. Absolutely. I don't have a number at the top of my head now, but they're extremely, extremely tiny, and they use, of course, amplification to sort of amplify the signal, and then you can actually see it. Just like in the case of gravitational waves, that's also something else. All those effects are minute. They're very, very, very small. So of course you need amplification to kind of do that.
Oh wow, yeah. I always thought that like I didn't realize that physics still has a long way to go to keep learning about different things. I thought that was it. I thought we discovered gravity.
I thought we discovered everything, and now we're looking up at the skies, right? Like that's what I thought.
Yeah, there's so many things. Of course, physics is a very exciting. I mean, I'm only talking about particle physics now. Imagine there are so many other fields.
Let's stay with the theoretical. Let's stay with the theoretical physics. This is another fun question. So, so from what I understand, a theory is only a theory until you give further evidence or is disproven, right? As for the theory of gravity, is that like a solid theory, or from what I understand, it has been disproven. So. And if okay,
the theory of gravity.
I guess Ali, can you pull up the UFO videos? I guess there's a time to pull up the.
Oh, we're doing this now.
Yeah, sure.
Like right now.
Yeah, just pull it up. Okay, I don't know if you saw the classified leaked videos of the UFOs by the Pentagon. So
I heard about these now.
Okay, let's show.
You heard about them.
Let's just show you the video.
Professor, you're about to have minus.
Yeah, no, I'm glad we're doing this now.
You have studied is about to be thrown out the window. Watch with a 2-minute video. All right. Let me give you a little bit of context before we dive in. So these are Navy, not even Navy. These are like Air Force pilots, and as you know, Air Force pilots, they pilot a plane that moves in ridiculous amounts of speeds and can do these certain aerial maneuvers that are on its own crazy, right? On their normal day-to-day, ventures of flying their plane, which is what they do, I'm guessing. It's not really an operation. It's just they take their planes out for a spin, basically.
That's it?
So-
Okay.
So they see
Mhm.
this foreign object flying in a way. Here, let me since I'm giving context. What they are looking at, they were looking at this foreign object, cigar shaped, as you'll see them described, moving in a way that like just defines physics that we know, basically. Like it's out of our
I mean, I don't understand.
understanding
Yeah,
of
from what I
physics,
understand,
right?
like the way it moves gravitationally is it just moves up, down, left, right, zigzag at super speed. So
Yeah, here, check
maybe
this out.
without any heat coming out of it. Ali, can you share sound maybe? Oh yeah.
There's just a YouTube guy
Cool, cool.
talking. So
Sounds good.
this is the object taken from
Wow.
the flight, right? Cigar shaped, as you can see, and it's moving in ways that are just crazy. Look at that.
Yeah, it is moving strange.
Like this is a very high speed, so they're barely keeping up with it, right? Look at the way it's tilting, it's moving.
So, okay.
Has this been confirmed to be real then?
Yeah, this
Yeah,
is
this
like
was
from
this
the
is released
Pentagon.
by the Pentagon.
Yeah, by the Pentagon. Mhm.
Like the actual Pentagon,
Do
right?
you really think, or do you see that the weird motion of it? I don't see it weird.
Yeah, we don't. Is there
Hold
any?
on, let me
I didn't see anything
Yeah, no,
weird
that is
about
no,
it.
that's fair.
I mean, the shape maybe. Look, they can barely keep up
Yeah,
with.
like you see that. Yeah, that is.
Here, let me open.
So it's very moving.
This is why I didn't want to share stuff.
All of these videos have been leaked in the past, but the US government now confirms they are genuine.
Look at
In a
that.
statement, the Department of Defense said it was
wow.
releasing the videos in order to clear up any misconceptions by the public on whether or not the footage that's been circulating was real or whether or not there is more to the videos. The aerial phenomena observed in these videos, they say, remain characterized as unidentified.
Unidentified. Wow. There you go.
Courtesy of Sky News, obviously. Please don't shut this video down.
So
Otherwise,
from what I understand, it has no heat. It has no propulsion system, and the way it moves, like it doesn't move linearly. It moves like zigzag, up, down, at like tremendous speeds. Like they barely caught it on footage. I don't know if you saw.
Right. Yeah.
So I don't know if what's the theory.
I mean, yeah,
I do not know about this stuff.
Even if those officials, yeah, I don't know either. If those,
Yeah.
you know, officials have no explanation, I definitely don't have any. I don't
That's
know.
fair.
But again, it would be strange if we were alone in this universe. It is definitely there's
I
definitely
agree.
something out there. But the question is, have they visited us? Did you have contact with them? That is something I don't know.
I have a theory
but,
about that.
What's your
There
what's your
must be
theory?
something there.
I think they probably visited us once, and they're like, "Yo, these guys are too dumb for us." And they're just
Could be.
out
Could be.
here.
Or,
like that's my theory. Because let's be honest, if they reached us before we reached them, that instantly tells me they are much more advanced than we are. We can't even find them, let alone reach them, and they found us, right? So I don't know.
Okay.
Listen to this then. If you're into theories, do you guys know about like New Age religion and stuff? It's completely absurd. Basically, it's like really good really good storytelling, masquerading as a religion. But anyhow, they have this idea that there's something called the tetrahedron square pyramid, and it's a shaped thing, right? So you can Google it. Just put tetrahedron pyramid and you'll see it. And basically, they have this idea that if you meditate long enough with the right crystals,
with the right crystals.
yeah, something like that. Basically, your third eye carries you in a tetrahedron that allows you to travel through space at tremendous speed, just like that.
Just like that.
For the people who are as
That's a tetrahedron.
equivalently dumb as I am, this is a tetrahedron.
Now, the shape is just
I'm
normal.
aware.
There's nothing special about it, but they just have this strange idea about it. And that's how they explain the pyramids and stuff. It's actually really funny. You should look it up one time.
I see. All right.
Yeah.
Since
If
we
you have some time to waste at some point, I will probably do that.
all right. Well, yeah. If you ever have also more time to waste, since I'll throw in one more in there. So, like spirits and stuff. Like I don't know if you can detect from Amir and I had an episode with a paranormal investigator. And, yes.
Okay.
Yeah, and from what we understood, there are ways to detect spirits and the afterlife and paranormal. So, anyways, if you have extra spare time, also.
Well, somebody asked this question to a physicist. I don't know, years back, and the answer came from a physicist from CERN, basically, that if ghosts were real and those, paranormal entities were real, we should have detected them at CERN, because our instruments are actually sensitive to a certain range of energy that if any of those things passed through, we should have been able to detect them, and we haven't detected anything. So
that's true. But ghosts are smart. Ghosts are smart.
Yeah, they avoid CERN.
They're probably gonna be like,
right. Yeah.
these guys are gonna put us out there, and we're trying to scare some idiots. So let's not, mess with the smart ones, right? That's probably what they're thinking. But speaking of time, time travel.
Oh wow!
I thought you were gonna say, speaking of time, time is up. Bye bye. Okay.
No. We got all the time in the world.
Speaking of time.
Time travel.
Sure, time travel. We're traveling through time right now, dude.
How
I'm in the present future now. Now.
Are we done?
Yeah.
Cool. How realistic is time travel, to go back in time or move forward in time? Please say very realistic. Please say very realistic. Please.
Well, I'm going to try to be sort of more scientific in my approach and to project my
yeah, be a scientist, even if it breaks my dreams. It's cool.
So, no, it's not possible to go backwards in time. That's there's a lot of paradox, but I always, whenever I ask a question which is a little bit controversial or it's still an open question in physics, I always tend to say, as of yet, it's not possible. I don't know, 50, 60 years ago, we wouldn't be even thinking about doing this conversation that we're doing right now. You might ask somebody back then, it was like, no, that's absurd. You cannot just talk to someone over,
a plastic,
yeah, on a screen, and you can see the person and hear them. So advancements in technology is always.
It's not just technology; it's also I think it's also our understanding of the sciences, right? Like before Newton, people tied themselves to their beds, right, thinking they would drift off into space if they fell asleep. But because an apple fell on his head, instead of making a mu'assal, he decided to study the whole thing, right? And it was like, you know what?
Yeah.
There's gravity.
Right. Yeah. I mean, of course.
Who knows?
Science is the basis here.
Right.
So I would say that at this point, even there are some paradox. There's a paradox that might come up by actually going backwards in time, which is if you go backward, let's say in time, what prevents you from, for example, killing your grandfather, and in this case, you won't be conceived. So basically, you will alter the future. So this paradox is still going. Now, I heard recently that someone solved it, but I was not able to read the paper yet. They put a paper. It's actually a peer-reviewed paper. It's something in quantum mechanics that there was a way in order to circumvent this dilemma of basically this paradox of going back and probably killing your grandfather and so on. So I don't know how they resolved it, but it seems it's resolved. So I don't know how would this apply to reality, but it's not very possible at this point.
Not yet.
Yeah.
I have a question for you. Like, how does pursuing physics change the way you look at life? Like, how does it affect you on a daily basis? Like, psychologically? When you look at things, are you always concerned with cause and effect, or
well, definitely, like pursuing physics and studying physics will discipline you in a way. I don't, tend to look at my, like, little things in life and just things that you shouldn't worry too much about it. Like, there are bigger things when you study, for example, there are far more bigger things in this universe, or even on Earth here, that than the little things probably you see in your everyday life. So yeah, it definitely changes you. It disciplines you. It makes you more mature. That's how I felt on.
I remember back at school, I came to you one time, and I was really excited about this book by Stephen Hawking. I don't know if you remember. It was A Brief History of Time, I think.
Yeah.
And I came to you, and I was like, and you were really excited about it. You're like, yeah, you should read more of his books. You should read the Universe in a Nutshell. And then I told you, like, okay, so what is a good quality for particle theorists? And I was telling you, he needs to be creative. And then you were like, no, he also needs to not be stupid.
Did I say that? Okay, probably I did say that.
Done. You put your teacher on the spot.
Probably I said that. I don't know in what context I said, like,
no, it was in a humorous way. Like, obviously you weren't trying to, like, disencourage me or anything.
Listen, whatever you say on this show, you can never be more offensive than me. Don't worry. I said some crazy shit on here. Don't worry about it.
What are some good particle physics books if you want to get an understanding of it? If there are anything that's easy.
So there's, there's some. It starts from the fundamental stuff. I think you can read those books by Feynman. Those are called the Feynman Lectures in Physics. They're good. They're actually old ones. Feynman is somewhere in the I don't know where he actually wrote them, but Feynman died I think in the 80s. But they're still relevant. And Feynman was known as a master of lecturing in physics, and making a difficult topic seem like very approachable and easy to comprehend. So yeah, the Feynman lectures in physics are actually good.
Yeah, definitely listening to you make it like sound accessible. It gets me excited about reading like the articles again and getting back into it, because it's been a long time since I've done things like that. So it's really nice to hear that you can still understand it, even if you don't understand the mathematics of it.
Right. Yeah, of course. I mean, once you have the background that you had in school and the common sense, then it shouldn't be too hard.
So I can't read the Good to know. If I can suggest a good physics book, this is also to the viewers watching. Astrophysics for People in a Hurry by Neil deGrasse Tyson. Those are one of my I don't know if you've read that, Amin, but that book is really good.
He's not in a hurry.
I mean, if you're ever in a hurry, you can listen to it.
No, Neil is definitely a very good physicist. He's a good communicator. Basically, he brings topics in physics, just like Brian Greene and those other guys.
Yeah.
They bring difficult topics in physics, and they try to make them more approachable to people, regular people who don't have background in physics. And he's a very good communicator, definitely. I haven't read that book. I've seen some of his shows, I think.
Star Talk.
He's very good.
It's a podcast by Neil deGrasse Tyson.
Yeah.
It's a really good podcast. It's one of those few ones I genuinely enjoy. Other than
he's very good.
This one, A to the show.
That sounds good.
Speaking of A2, boys,
yes,
I think.
I just wanna ask one more thing. So you just made me self-aware right now in that moment. You mentioned something about like we wouldn't have imagined that we can have like a Zoom conversation with us talking. Last time I saw you was in the human flesh, and now I see you in data ones and zeros. So I'm gonna give you my basic understanding of what I think is happening right here, and maybe you can tell us a little more. So there's light, gets captured by my camera. Gets transformed to like data code, gets sent to space through my Wi-Fi. Satellite
Okay.
bounces it around, finds Amin's whatever zip code, connects
Right,
us.
or
At this point, I'm
Antenna
lost.
dish.
IP
It
address
finds
or
your IP
something, yeah.
address, right? And then the same thing
Yeah.
for your camera records your light, and then your face, and then your audio records your sound, and
Right.
it does the like, it processes it inside and outside. Yeah, I'm kind of So am I right?
I mean,
Pretty
yeah, in
much.
principle, that's right. That's the skeleton of it. But of course, the intricate details are far more complicated when it comes to data processing, which is I'm not an expert in. When my expertise ends with light capturing your image, and then when it's being transported to the computer, this is a whole new world.
When you can actually see the things, his expertise stops.
Yeah, that's right.
Okay. So yeah, we've hit our timestamp, boys. This was fun. It's nice to meet you, Professor or Doctor Amin.
Thank you.
said
Same
your
here.
title, so I'm kind of confused.
Don't worry about it. You can say anything.
Boys, this has been fun. Physics
Yeah, this was-
itself is pretty chill, right? Thank you for watching another
Thank you
episode.
for
If you
watching
did
another
enjoy, please do
episode.
subscribe, like, share.
Make sure
It's
to
very
share and
important.
subscribe. Those two things.
Yeah, those two are very important.
What happens if you don't subscribe? I mean,
What happens if you don't subscribe?
Well, you won't get the notifications of
you think of it too
Basically-
literally. You sound like theoretically.
Physicists, am I right, boys?
You lose your electrons or something if you don't. Lose your cards forever.
If you don't subscribe, you lose your electrons. Peace, love, happiness.
Wait, make sure that I mean, is there anything else you'd want to shout out or say before?
Let the world know. Or
I just want to say thank you for this. It was great seeing you again and meeting Ali.
Yeah, it was really nice catching
I don't know
up.
if you guys had to change this to 8 cubed or you're just gonna keep it 8 squared.
I think it's a to the power of 4 now.
The power exactly. Too many 8s here. Yeah, it was been nice catching up with you again.
Well, a to the power of 4 will put quantum physicists in a whole new dimension of studies. Until that happens,
Thank you.
myth number 3 says your brain adapts so that it can function just as well on less sleep.
That's a myth too.
That's,
He knows it. She knows
I
She knows the
guess.
facts.
okay.
Yeah, the brain can adapt. I'll give it that. Like,
The brain is flexible.
It's a half myth.
Yes.
The brain is flexible. The brain can adapt if you don't have enough sleep. So think about mothers with newborn babies. They'll be sleep deprived for a long time. So their brain can adapt.
Oh.
But
Not for long.
it should be a temporary. Yeah, it should be a temporary